Well, good day to you. I hope you're ready for another podcast from me. I'm Chris Clements, teacher at Caddo Parish Magnet High School in Shreveport, Louisiana. I'll be talking to you about colligative properties on today. Colligative property is a physical property of a substance that is dependent upon the number of particles present in it rather than upon its size, mass, and characteristics of those particles. Those factors will include what the solvent is, what the molality of the solution is, in some cases what the molarity is, and what the polarity of the solute is, meaning how it dissolves in a solution. There are 4 colligative properties. I will end up discussing in greater detail 2 of them, but the first 2 I'm just going to breeze through. The first of them is vapor pressure. Vapor pressure is defined as the pressure of particles sitting above a liquid. We know that as we increase temperature, we'll increase the number of vapor particles that sit above a liquid. And if we put a solute into a particular solvent, in this case a liquid solvent, then what we're going to do is reduce the vapor pressure of that solution compared to the vapor pressure of the pure solvent. It's known as Raoult's law. Pardon that bell. I am recording this at school, so you get to hear what our bells look like. Okay, the second colligative property is osmotic pressure, and osmotic pressure is the pressure required to just stop osmosis from occurring. If you recall from a biology course, osmosis is the migration of liquid through a semi-permeable membrane. We tend to talk about osmosis through cell membranes, for example. And the 2 colligative properties that I will be discussing in greater detail today are freezing point and boiling point. The freezing point of a substance is defined as the temperature at which its liquid form turns into a solid. And by the way, a lot of folks will get confused and think that a melting point is different from a freezing point for a particular substance. No way, they are both the same. So you guys should know that the freezing point of water is 0 degrees Celsius and the melting point of ice is 0 degrees Celsius. So that's a pretty helpful little tidbit, huh? All right, the new freezing point of a solution, which will be different from the freezing point of the pure solvent, is determined by considering what that solvent is, what the molality of the solution is, and then the level of dissociation of the solute. So we'll look at all 3 of those factors and get them all pieced together by the end of this podcast. The most common solvent is water. I believe most of you probably know that. And knowing what the solvent is enables us to put one part of the puzzle piece into this. So the freezing point constant is something we will have to know for every solvent that we use in any of these problems. And since water is so very prevalent and such a universal solvent, we might as well just commit the freezing point constant for water to memory because you're going to be using it quite a lot if you work lots of these problems. We represent the freezing point constant for water with a lowercase k and a subscript of f, read as kf. So the kf of water has a value of 1.86 degrees Celsius times kilogram over mole. Again, 1.86 degrees Celsius kilogram per mole. The next part of the puzzle is knowing the molality of the solution. So, a little reminder on molality, if you don't recall that from your solutions podcast that you hopefully listened to. Molality is represented by a lowercase m, and it is determined by taking the number of moles of solute and dividing by the number of kilograms of solvent. The third factor that takes a little more explaining is the level of dissociation of the solute within the solution. It's represented by what's known as the Van 't Hoff factor, represented again by a lowercase I, which is typically italicized. I'm going to go over how you determine what the value of I is now. Covalent compounds, those that are bonded in a covalent or molecular manner, do not dissociate in solution. A prime example would be taking glucose, which is C6H12O6, placing it in water. It's not going to dissociate to yield 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Instead, it remains as one molecule of C6H12O6. So you might have lots of molecules of C6H12O6 floating around within your water, but you're definitely not going to have carbon atoms, hydrogen atoms, and oxygen atoms. So the Van 't Hoff factor for any covalent compound is 1. It is unitless. It's just a number. And remember that you recognize covalent compounds because they're made of 2 or more nonmetals. If, however, we're dealing with an ionic compound and it's dissociating in water typically, we need to recognize that most ionic compounds will dissociate in water. I'm going to go over several examples, first of which is NaCl, sodium chloride. Sodium chloride will dissociate to yield one sodium ion and one chloride ion, and I get that from its formula, for every one formula unit. So if I add that I have one sodium ion and one chloride ion, then that means I have two total ions floating around for every one formula unit. That means its Van't Hoff factor is 2. The Van't Hoff factor of any ionic compound will therefore be determined by the number of ions that it yields. And remember, you recognize an ionic compound because it's made of a metal bonded to a nonmetal, or, of course, take into consideration that there can be some polyatomic ions in there. And I'll give you an example of that in just a moment as well. So if I ask you for the value of I for calcium chloride, you should first think about what the formula of calcium chloride is. And you should hopefully come up with it's CaCl2, because there's one calcium ion and there are two chloride ions. When we add that together, we get 3 as the Van't Hoff factor. For aluminum chloride, we again think of the formula. It should be AlCl3. One aluminum ion plus 3 chloride ions gives us a Van't Hoff of 4. But if I ask you to give me the Van't Hoff of something like sodium sulfate, well, that formula is Na2SO4. When it dissociates in water, it'll form 2 sodium ions and 1 sulfate ion. That sulfate ion, you recall, is SO4, 2 negative. So my Van't Hoff factor for that is 3. Don't get confused by all those subscripts that you see in polyatomic ions. Think of a polyatomic ion kind of as a covalent compound that went bad. It couldn't quite get everything balanced charge-wise, so it just hung out with the charge. So don't break them apart, just like you would not break apart a covalent compound. Now, when we piece that information together, we get the freezing point depression formula that we will use to find what's known as the change in freezing point. That change in freezing point is represented by delta uppercase T subscript F. So I'm going to read you the formula, and you can write it down, or you can look at my PowerPoint along with me if you wish to. It is delta TF equals KF times M times I. That means I'm going to multiply the freezing point constant by the molality, by the Van't Hoff factor, and I'm going to get what's known as a change in freezing point. Well, I'm not quite finished at that point, because what I have to understand is that change in freezing point must be subtracted from the original freezing point of the solvent. So my next formula that I use reads TF of the solution equals TF of the solvent minus delta TF. And that will end up giving me the freezing point of the actual solution. So I do have to know the freezing point of the solvent. And again, keep in mind that the freezing point of water is 0 degrees Celsius. Okay, so the next thing we're going to do is look at boiling point elevation. And boiling point is defined as, of course, when a liquid turns into a gas, the temperature at which that occurs, that is. And to avoid confusion, the condensation point is that same temperature at which a gas turns into a liquid. The boiling point of water is 100 degrees Celsius as long as we have standard atmospheric pressure of 1 atmosphere, and the condensation point of steam is 100 degrees Celsius as long as we have standard atmospheric pressure. But when we add a solute to a solvent, then we end up increasing the boiling point. That mixture, the solution's boiling point, will be greater than that of the pure solvent. The new boiling point is determined again by thinking of those same 3 factors: what the solvent is, the molality of the solution, and the Van't Hoff factor. The boiling point constant that we will use for a solvent is represented as Kb. That's a lowercase k with the subscript of B. And the boiling point constant for water, again, should probably be committed to memory just because you tend to use it much more so than you use any other solvent. The Kb of water is 0.512 degrees Celsius kilogram per mole. When we piece all of this together, we're going to get a very similar looking formula to what we just had for freezing point stuff, but it's going to read delta Tb equals Kb times M times I. And since we know that the boiling point is elevated, or will be higher than the boiling point of the pure solvent, we're going to figure out the boiling point of the solution by adding our change in boiling point to the normal boiling point of the solvent. And that formula reads Tb of the solution equals Tb of the solvent plus delta Tb. Okay, now, if you listen to my first podcast, I was confused on what my internet address is for my website, but if you will go to http://KRISCLEMENTS.googlepages.com, you will see that I have PowerPoints uploaded for some of my Chemistry 1 students, and you are welcome to look at the Colligative Properties PowerPoint and go through the couple of problems that I have on there. I will also have a practice sheet for Colligative Properties under that same Chemistry 1 Honors Stuff heading. Hope you've gotten a lot out of this, a little bit of information. I'll keep doing these podcasts and enjoying doing them. Thank you much for joining me. Have a great day.